Hey everyone, we are continuing with Physical Sciences, Grade 12, November 2023, Paper 2. That's chemistry. We've already covered the first four questions in previous videos, and now we're going to look at question 5. So, diving right into it, question 5 has got a bit of preamble here that we got to read. They give us quite a bit of information. So let's go through it and make sure we highlight any important information before we get to the actual questions. So the reaction between dilute excess HCl, excess is very important here, um, and sodium thiosulfate is used to investigate factors that influence rate reaction. Okay, so we know that this is a question to do with kinetics because we're already talking about reaction rate. So they give us the equation. Carrying on, the concentration of HCl used is 1 molar. Okay. The same volume of HCl is used in each run. All right. Um, the time taken for the cross on the paper under the flask to become invisible is measured. So that's how we measure our reaction rate. Once the reaction gets nice and cloudy due to the formation of products, then we know that the reaction has reached a certain point, and we can use that to time each reaction, so how long it takes. So this is a pretty cool setup to just measure reaction rate, fix one variable, that's HCl, and then vary another one, uh, which is exactly what they've done here with the volume of sodium thiosulfate. Okay, so getting into the questions, define reaction rate. So there's a couple of ways to say this, but what's important is that you talk about a change in either concentration, amount of matter, so moles, volume, mass. Any of those variables can be used to measure a reaction rate, but what's important is change. And it would be in the any of those variables just mentioned, either in the products or reactants. So you can measure reaction rate with respect to products or reactants. I'll just say RXN for short. And then the last bit that's important is to say per unit time, because it's a rate. So it's a change per unit time. In the question, they are using seconds as their unit time, and they are measuring the reaction rate, well, for example, in CM3, or in the amount of sulfur, which could also be in volume, or how quickly the solution goes cloudy. But yeah, okay. So moving on to question 2, write down the independent variable for this investigation. Well, as we just said, we are fixing HCl. HCl is fixed, and we vary sodium thiosulfate. So the independent variable is the concentration of sodium thiosulfate. Okay. Question 3, calculate the value of P in the table. Okay, so first of all, they don't tell us the concentration of sodium thiosulfate, so we need to figure that out. And we can just use, or we don't need to exactly figure it out. We can just use the algorithm C1V1 equals C2V2. So what we need to see here is that we have enough information about the concentration of sodium thiosulfate here and its volume, um, that we can calculate the unknown concentration using this algorithm. So let's set it up. So there's 3 different ways you can set this up, but I'll just choose the easiest. So we'll take the first concentration, which is 0.13, multiplied by the first volume, which is 50 50 milliliters, but Or you can set it up the other way, because we need to invert them to find the unknown. So we can put the volume something like this. We like sort of cross multiply. So we can put the volume of the unknown one here, because we're going to cross multiply anyways. And then the unknown concentration multiplied by the other volume, 0.05. Okay, so rearranging, we get C2 equals 0.078 molar. This is pretty straightforward. It's just a matter of deciding which way you can do it. You don't have to use the numbers from run 1. You can use the numbers from run 2 and then just cross multiply to get the unknown. You can set it up whichever way. So I've just shown the one way, but there are a lot of other ways that this can be done. All right. So maybe let's just write this down for future. So we said 0.078. We might need this later. Capital M and moles per dm3 are the same thing. They both just mean molarity. All right, so moving on to the next question. When 0.21 grams of sulfur has formed in run 1, the cross becomes invisible. So they're basically telling us when the reaction ends. So the reaction ends when we've produced 0.21 grams of sulfur. Okay, so this is important because this is when the reaction ends. Calculate the average reaction rate with respect to sodium thiosulfate. Okay, so it's telling us with respect to, we need to calculate the reaction rate with respect to our reactant, not the product, and we need to calculate it in grams per second. So if we were to calculate the reaction rate with respect to our product, they've already given us enough information to just say 0.21 grams of sulfur, and then the time given for, let's say, run 1, 20.4 seconds, and that'll give us a rate in grams per second. And then you can just do it for all 3 runs and get the average. But the trick to this question is that it's not with respect to sulfur, but rather with respect to sodium thiosulfate. So we first need to figure out the mass of sodium thiosulfate used for each for any run, because the same mass of sodium thiosulfate will always give the same mass of sulfur. So we just need to work back once, and then that same mass would be used up for the different times, and then find the average. So let's work back. Okay, so how do we find the mass of sodium thiosulfate? So first of all, we know that the ratio of sulfur to sodium thiosulfate is 1:1 from the chemical equation. So if we calculate the moles of sulfur, that's equal to the moles of sodium thiosulfate. Okay, so let's calculate the moles of sulfur. So moles or N equals mass over mR, or molecular mass, so mass over molecular mass. And this is given as 0.21 grams. And then if we just look up the molar mass of sulfur, that is 32 grams per mole. It's always good to include units just to make sure that your answer makes sense. It's a good way to just check yourself. And then using a calculator, we can figure this to be 0.0065625. And then don't drop any significant figures. You'll round off at the end, and this is in moles. So now that we have this, so we know the mass of sodium thiosulfate, well, the moles is equal to this. So let's calculate the mass of sodium thiosulfate because the answer is in grams per second. Okay, so let's just make some space down here. So the mass of sodium thiosulfate, rearranging our equation, we know it's moles times molar mass. So we carry our answer from before times the molar mass of sodium thiosulfate, which molar mass of sodium thiosulfate, if we can just look this up real quick, it's 158 grams per mole. So this was in mole, grams per mole. You can see that our units of mole cancel and we'll be left with grams. So multiply that by 158 and we get we get 1.03875. And we're not going to just drop any significant figures just yet. So this is grams. And then what we need to do is divide each. So divide our mass of 1.0368 by each time and find the average. So let's do that up here. So for the first one, we have a time of 20.4 seconds. And that gives us a rate of roughly 0.001. Let's just keep 4 significant figures for now. Okay, grams per second. And then for the next one, we have 26.7, which gives us 0.0009363. And then finally, for the last one, we have 33.3, which gives us 7507. And then if we take that average, so add all these up, and divide by 3, we get an average rate of about 9.707 times 10 to the minus 4 grams per second. And that's our final answer. Yeah. So there are again a couple of different ways you could go about this, but this is the simplest way I feel. Let's just double check, calculate the average reaction rate with respect to sodium sulfate. Okay. So what we've done is we've calculated some overall reaction rate, but you really only need to do this just for run 1. So just using the time of 20.4. So the final answer would have been this first one alone. But yeah, it's just a good thing we did all of them just so that you can appreciate how it's done. Let me just clean all this up and get rid of it. Yeah. Okay. All right. So moving on to the last 2 questions. So these are sketching questions. Okay. Sketch the Maxwell-Boltzmann distribution curve for the reaction at 20 and label this curve A. On the same set of axes, draw the curve that will be obtained at 35 and label it B. All right. So what's a Maxwell-Boltzmann distribution curve? What does that include? So let's put a set of axes. use a ruler for this. I'm just using freehand. At the bottom, we have kinetic energy for this plot. And at the top, we have number of particles. Number of particles. I guess sometimes you can also see this done where there's moles, but number of particles is just more direct. So it wants us to sketch the Maxwell distribution for the reaction at 20 degrees Celsius. So any distribution, um, yeah, so the main point here is like not how you actually draw it. We know that at all the different temperatures, it'll look something like this. Um, but what's important is to show the comparison between the two temperatures. So what you got to remember is that actually at a higher temperature, um, there will be more kinetic energy. So as you can see, for the first one, so let's say this is the one at 20. So 20 is in blue. We can see that right about here, our kinetic energy is kind of low. So at 34, we're going to have more kinetic energy. So we're going to have our peak, so the highest part of the curve, be somewhere more to the right because there's more energy. This is at 34. So however you draw this, you just have to make sure that the higher temperature basically is just has its highest point more to the right because it's more kinetic energy at a higher temperature, and that's basically it. Okay. Let me just clean this up real quick. Okay. Let's look at the last part of this question. Explain the effect of temperature on reaction rate in terms of the collision theory. Okay, so this is basically what the Boltzmann distribution we just drew was showing us. And oh yeah, by the way, so you have to make sure you draw two axes and you put arrows to show which way is increasing, and you have to give them axes titles. So kinetic energy, number of moles, and then you have your two plots and you label them A and B. So that's what you got to do for the full marks for 5.5. Going on to 5.6. So, in terms of collision theory, there's a lot of different ways you can phrase this, but you just have to include these couple of key phrases. So, the collision theory is basically at higher temperature, particles move faster and have more kinetic energy. Therefore, more molecules have enough sufficient kinetic energy for an active collision. So, where it can collide with another molecule and react. So yeah, it's basically correlating higher temperature means higher kinetic energy, which means more collisions, which means faster reaction. So yeah, you can package that into a little paragraph or a couple sentences that are coherent and make sense, but you just have to include those those couple key ideas in however you answer the question. And yeah, that concludes question 5.